Hello, Honors Algebra 2. Today we're going to talk about Edgenuity Section 10.4 called Properties of Probability Distribution. We have three objectives: to identify properties of a probability distribution, to create probability distributions from a set, and to solve problems using probability distributions. So let's take a look at our first problem. All right. So we've got what we call a fair spinner. It's like the spinner that you use in certain board games and well, lots of other things, right? It's kind of like a real simple version of the wheel, fortune wheel, that sort of thing. Okay, and we're going to answer some questions about this. The first is, what is P? What is the probability of getting yellow? By the way, those letters stand for colors, yellow, blue, green, and red. And the question is, what's the probability that when you spin this fair spinner, you land on yellow? Well, there's four colors. Yellow is one of them, so the probability is 1 in 4, or you might call that 25%, or you might call that 0.25. It's one of the four colors, and since when you hit the spinner, it spins what we say fairly, which means that we're going to get a true random outcome, that is, everything is equally likely, then it is just one out of the four equally likely things that could happen. So chances, the probability are 1 out of 4, or 1/4. Okay, so then what about B? B asks for the probability of a yellow or a green outcome. So the way you do this is you take probability of getting a yellow plus the probability of getting a green, which is of course 1/4, plus another 1/4, and that is a consequence that the or is what tells me to add. Okay, typically in probability, if you say or, you're going to be adding. Now, sometimes it's a much more complicated addition problem than this, but it kind of boils down to, if you say or, then you're adding. That's not a very good plus. Let me make that a little more obviously a plus. There we go. So 1/4 plus 1/4 is 2/4. You just add the ones. And then 2/4 can reduce by 2. I can divide each part of those by 2 to 1/2, or 50%, or 0.5. So the probability of this is 1 out of 2, or 50%. Okay? Then finally, what is the sum of the probabilities for all possible outcomes? So think about it this way. It's 1/4 for yellow, plus 1/4 for blue, plus 1 in 4 for red, plus 1 in 4 for green, which is 1 plus 1 plus 1, which is 4 out of 4, or 1. Or 100%. And that should make sense, right? If I say, all right, what is the probability that you spin the spinner and it lands on one of the colors, any one of the colors? It's 100%, right? It's got to land on one of the colors Otherwise, something really weird happened, like, I don't know, it didn't, the spinner fell off or something weird like that. So, definitely, if you, all the outcomes, all the probabilities, when you put them all together, they have to come out to 1, right? There is another little detail to this, and it's going to come up later, and I'll revisit it then, but there is another little detail, which is that probabilities are not negative. You can't have a negative probability, not in most cases. I won't say never. I'm not actually a statistician. I'm a mathematician. So there may be some weird time out there where you can have a negative probability, but in the usual cases, in the cases that we're going to talk about here, you won't get a negative probability. Okay. So let's talk about this fair spinner idea again. So right here is the set, which we're going to call S, capital S, of all possible outcomes if I spin it twice. Okay, I spin it, record what I get, spin it again, record what I get, and that's one trial. Okay. So I could have red, red, blue, blue, yellow, yellow, green, green, red, blue, blue, red, red, yellow, and so on and so on. Okay. So if you look at this, I've got a table here, and this table tells me, it's called a frequency table, and the frequency table here tells me the number of times that I get a yellow. Okay. So there are 9 times where I get 0 yellow outcomes. Okay, so that is, if you went through this and counted how many of them that there are without Y's, like all of those, you'll see that there are 2, 4, 6, and 3 is 9 of them. So, and how many times do I get 1 yellow? I get 1 yellow 6 times, right? And how many times do I get 2 yellows? Well, there's only 1 time where I get 2 yellows. That's right there. Okay. So now the question is, what is the probability of only 1 yellow? So here's the thing that I'm looking at. Okay. So the probability of 1 yellow, the probability of anything else and a yellow, provided that anything else, actually maybe I should be more careful with that. Let me be more careful. The probability of having a green or a blue or a red and a yellow. We could say it like that. So 1 yellow happens 6 times. So it's 6 times out of however many total trials we have, spin possibilities we have, which just means adding all those up. And if you do 9 plus 1, you get 10, and then plus a 6 is 16. So then we might reduce that by, say, 2. And you might put this into a calculator, but I'm not big on just putting these into calculators. And in Edgenuity, if they're looking for a decimal, just put it into a calculator. But probabilities are perfectly legitimate as fractions. Don't ever forget that. Okay. So that gives us 3 out of 8. So probability of 3 out of 8 times that we're going to get a single yellow. And again, we could put that as a decimal. We could turn it into a percent. I will leave that to you guys. All right, I'll pause for a moment, give you a chance to look at that. And let's move on to the next question. All right, for the same spinner scenario, let's make a graph, let's make a table kind of like this one. It won't be a frequency table, but it'll be kind of like that, showing the probability distribution for green. So probability distribution is different from a frequency table. So the frequency table would look like this. Number of times that we're going to get green versus the frequency of those. We might get green 0 times, 1 time, or 2 times. And so we can go back here and we can count how many times we get 0 greens. There's 3, there's 4, there's 2 more, and the rest have green. And if you count, of course, as you might expect, you get 9. 2 and 3 is 5, plus 4 is 9. So you get 9 times that we get 0 greens. If you count the times we get exactly 1 green, you'll see we get 1, 2, 3, 4, 5, 6. Just like in the other one. And there's only 1 time that we get 2. However, this is not a probability distribution. So how would we make a probability distribution table instead? Okay, we're still going to have green, but now we're going to talk about the probability of getting green. And we want this in either percents or decimals. Let's do it in decimals because that's the way that Edgenuity does it. So we're going to need a calculator here, and we might want to remind ourselves that the total is 16 possibilities, right? So I'm going to take out my calculator, and the green side will be the same. 0 times that you get green, 1 time that you get green, or getting 0 greens, getting 1 green, getting 2 greens. Okay? And then I'm going to take my calculator, and I'm going to take each of those frequency numbers, and I'm just going to divide them by 16. So the first one, 9 divided by 16, so that probability is 0.5625. Now, again, I want to mention that you could be doing these in fraction form, but Edgenuity wants you to do them in decimals, so I'm doing them in decimal. Probability of getting 1 green is 6 over 16, so that's 0.3375. And the probability of getting 2 of them is 1 out of 16, which is 0.0625. And there we have a probability distribution table or graph. All right, I'll give you a moment to look at that. This is the actual answer that we want. I'll give you a moment to look at that. And let's move on to our next problem. Okay, let's move beyond the fair spinner, and let's talk about a situation where, okay, so we're going to sell raffle tickets, okay, at some event that we have. And we've got 100 tickets. We're going to sell, we're going to assume that we sell all 100 tickets. We're going to sell them for $10 a piece, and the reason people are going to pay that amount is because we're going to provide cash rewards out of this, okay? We're going to, at the end of the night, we're going to pull one random ticket, and whoever's ticket that is, whoever's ticket that matches, gets $100. Then we're going to pull 4 more, and we might do this in the reverse order. I don't really know how the psychology of all that works. But we're going to pull 4 tickets, and each person's going to win $50. And we're going to pull 10 tickets, and each of those people are going to win $30. Okay? So think we're selling 100 tickets, $10 a piece. This isn't really part of the statistics problem, but just thinking about all this, that gives us $1,000. Then we've got 100, and 4 50s is 200, so that's 300, and then 10 30s is another 300. So we're giving away 600 of that $1,000, so we're only making $400 off of this. Maybe $400 is our goal. This would be a very good way to guarantee a goal like that, right? And then the remaining money gets donated to the school. So if we're looking to donate $400 to the school, this would be a really good way to sort of ensure that that happens. So let's create a probability distribution table for this. The frequency table, again, is a good way to start that. So let's create a frequency table first. We'll have the cash reward and the frequency that it's going to happen. Okay? So $0. Well, how often is that going to happen? Well, we might want to know our total first, so we can sort of figure that out. So our total is, we've got 100 tickets, right? So then we got to take away each of these. We're going to pull 1 ticket for that, 4 tickets for that, 10 tickets for that. That looks to me like 15 tickets, leaving me with 85 tickets. So 85 times the 85 of the tickets that are in the drawing don't get drawn, right? What about for $30? $30 is for 10 tickets, right? What about for $50? That's 4 tickets, and $100 is only 1 ticket. So if we just divide those by 100, and that's really nice because that gives us really nice percentages and really nice decimals, right? So let's have our probability distribution, and we'll still have the money, and now we'll have the probability. making that money. So, probability that you buy a ticket and then make $0 off of it, that your money is being donated to the school, is 85% or 0.85, right? Probability that you put in your $10 and you win $30 is 10 out of 100, 10%, or 0.10, right? Or 0.1 if you prefer. But I think this is how they show it in Edgenuity, so I'm going to try and be consistent there. The probability that you win $50 is 4 out of 100, or 4%, or 0.04. Remember to turn a percent into a decimal. You find the decimal and move it 2 places smaller and fill in with zeros. So that's how I get 0.04. Okay? And the probability of winning $100 is 1 in 100, 1%, or 0.01. So there's our probability distribution table right there. I'll give you a moment to look at that. And let's move on to our next question. All right. Which of these represents a valid probability distribution? So, again, the rules about probability are no negative probabilities, and they have to add up to 1. So, let's look, for example, at C. Focus on C. Focus on the fact that there's a probability over 1 right in it, which means if we add all these up, we're going to get a total probability over 1. So, no. Right? So, no. Look at B and D. Both of them. Negatives. Negative. So, those can't be right. Which leaves us with A. Let's double check everything in A. Do the probabilities all add up to 1? When I add them all up, 0 plus 0 plus 0 plus 1 is 1. And no negatives in it. So this is, even though it looks kind of weird, why would you even be considering the probabilities of 0 things or 1 thing or 2 things when the only thing that you can possibly get is 3 things? I don't know, but it is a valid probability distribution, although maybe a confusing one. All right, I'll give you a moment to look at that. And let's move on to the next question. So, what is the probability of getting a 3 here? Well, that is the probability. You just pair them up, kind of like points on a graph. When you see them on a table, you just pair them up. So, probability of a 3 is 0.2, or you might say 20%. Or you might say 1 out of 5 if you really know your stuff, right? What is the mean of the probability distribution? Okay, so the mean probability is the average probability. And one of the ways to look at and see that is if I were to make a graph where I'm like, okay, so here's the 0 at 0.1, and then here's the 1 at 0.2, and then here's the 2 at 0.4, and then again and again for 3 and 4. So these curves, when they look like that, when they're symmetric like that, then two things that you know right away. If it's in the middle, the mean or the median is at the top of the hill, and the mean is in the middle. So this tells me that the mean probability is 0.4 or 40%. All right. I hope that makes sense. I'll give you a chance to look at that. Let's move on to the next problem. For the next problem, we're going to talk about, and this is where statistics really gets used a lot, is in industry. Let's say we're in a factory that produces parts. There's always some statistician working for companies that's figuring out this sort of question. The question that a statistician figures out for companies is, how often should we shut down the machines and recalibrate them because they're producing too many defective parts, okay? And there's a whole process to that, and you will learn it if you take like a first introductory course to statistics in college. You'll learn how to do that. And then the second course that you usually take is even more involved in that, and then there's specialized statistics courses and things like that. But so the question is always, do we have to shut down the machines, or are we okay with the number of defective parts that we're making that we have to throw out, that we can't use? Okay. And you're always making some amount of defective parts. You just want to reduce it. You want to minimize it. Thinking that you're going to completely get rid of them is not really realistic. Okay. There's always defective parts. So the question starts becoming, how often do we have to shut down the machines? And of course, every time you shut down the machines, you're sacrificing money. So when we get to that point, one of the things that you can start asking yourself are these types of questions. What is the probability of having two defective parts? And we've got a probability table here, and you need a probability table for this. What is the probability of having two defective parts? Well, here's the number of defective parts right here. Here's the pairing with 2. So A, it's pretty straightforward. 2 defective parts is 0.04. That is, well, let me write more than that. That is to say, the probability of 2 defective parts is 0.04 or 4%. Now, that's a big percent. You would want to shut everything down. Usually you want it to be like 0.05%, or at least 0.5%, something like that. 4%. Think of that if you manufacture 100 of them, you're going to be throwing 4 away. If you manufacture 1,000 of them, you're going to be throwing 40 of them away. You don't want to do that. You want to throw like 5 of them away for every 1,000 that you produce, right? And I suppose it's depending on what you're producing and stuff like that too. So then let's talk about part B. What is the probability of finding a defective part at all? Okay, so this is where you can be clever. This is where you can be really clever, because the probability of finding a defective part at all is like almost the reverse, if you want to think of it that way, of never finding a defective part, right? And we know the probability for never finding a defective part. So I'm going to make a note here. Note, the probability of 0 defective parts is 0.85, 85%, right? So the probability of any defective parts, the probability of any defective part is 1, that is to say 100%, minus that probability of finding 0 defects, right? Because if I'm finding anything at all, then I'm not finding 0 defects, right? 0 defective parts. So if I find 1, I find 2, I find 3, and that's really all the possibilities that we have here, then you're talking about having to think about whether to shut things down and that. So when I do this subtraction, and you can do this subtraction on your own, but you'll find that it's 0.15 or 15%. And one of the ways that statisticians would interpret that is there's a 50% chance that as we're going, or a 15% chance, sorry, that as we're going down the line, we're going to produce defects. And I want to tell you, in a factory, for a statistician, that's a really high number. Like, that means that 15 times out of every 100 runs, if you were going to check for defects 100 times a day or 100 times a week, something like that, 15 times you would find defects. So that means, okay, let me try and put this in super realistic terms for you. You're producing something that you're packing into boxes, right? So they come down an assembly line and they get put into boxes eventually, and they get put at the end of the line, right? And it's somebody's job to randomly take a certain amount of those boxes and check for defects, okay? And we might get no defects, we might get 1, we might get 2, we might get 3, according to this very simple model, right? And just to make things simple, let's say in a week, you produce 100 boxes. 15, or well, let's say in a week you check 100 of those boxes. You're going to make more boxes than 100. But let's say you check over that week, you're going to check 100 of those boxes for defects, for defective parts in the box. 15 of the boxes that you check are going to be defective. That isn't even counting all the ones that you didn't check. That's super high. That would not fly. Okay, just so you get an idea of where this goes and where this becomes important. So I'll give you one more moment to look at this. And let's move on to the next problem. This is the final problem for this section. All right, let's talk about a probability distribution graph and how it's skewed, how we compare things to the median, all that. Okay, so so it kind of looks like that if you were to kind of like that. Let me draw it even better. Looks like that, right? So the question is, first, how is this skewed? And the answer to that is always like not what you expect, the opposite of what you would expect. Okay, so let's have a center here. And so the majority of everything is over here to the right of the center, right? Right, if you were thinking on like a graph where this was the 0 point, the middle point, then this would be the negative side, this would be the positive side, right? So the skew is always like where not much is, okay? And the way I always have to think of it this way. I have to look at where it all is and say the skew is the opposite of that. So this is skewed negatively. Skewed negative. Okay. And then the other thing is that middle is the mean, and where the top of the hill is the median. And so for this particular one, the mean is smaller than the median, right? The median's larger. You can see that. And then finally, how do we compare the mode and the median? The mode is the one that occurs most frequently, which is going to be that one right there, right? And the median is somewhere with that one, but the mode, so how do you get the median? The median is like the middle number, right? So it's going to be somewhere. It's going to be either 5 or 6, or it's going to be 5.5. So, and I don't quite remember how Edgenuity has it, but I think it would be fair to say that the mode is either going to be greater than or equal to the median. You'll want to double check that with Edgenuity, but I'll give you a moment to look at that and think about that. And that is the last problem for this section. Thank you so much for listening. I hope this has helped.